This video is going to show you how to run a simulation in Crystal Grower for a net-based crystal structure. So the types of crystals that you might be looking at for a net-based structure are molecular crystals or ionic crystals, or some metal organic frameworks. There's also a video for tile-based structures, so if you want to learn how to simulate those, then have a look at that video. The first thing we decide is whether it's a net or tile simulation. So like we've said, we're going to simulate a net-based crystal. And then we need to browse to find our structure file. We need to tell the program what crystal structure we're going to grow. So we're going to browse here and look for the crystal structure file. We're going to look at urea because that's quite a simple one to start with. We can click read structure file and we'll get a prompt to say the structure file has been read successfully. Now, one of the key differences when you're looking at a net crystal structure versus a tile crystal structure is that we need this additional file which contains our energies to assign these interactions between the molecules in the structure we're looking at. Whenever you partition a crystal structure in Topos, it also generates a corresponding bonds file which will contain the interaction energies between your species in your crystal structure. So if we browse and find that, I have one prepared already for urea, which is this one here. And I can click read net.txt and it'll give me some information about the interactions in the crystal structure. So you can see there are two urea molecules in the unit cell. We use the primitive unit cell. And it lists the interactions between the species and assigns them an interaction type with the letter. So you can change these if you want, but we'll leave them as they are for now. So what this is telling us is if we change interaction 1 here, we're changing interaction type A, so it'll also change the corresponding interaction on molecule 2. And the same for every other interaction. This is correct because the interactions are defined by the molecule point group, so provided the coordination's the same in the molecules, they should be treated the same. And Topos automatically picks this up, and so does the user interface. So we'll confirm the interactions here, and later on we'll get to changing the energies on them. So this time we're not going to add any optional features, we're going to just stick with no screw dislocation, and you can also add stuff like growth modifiers, so poisoning agents, but we're going to leave that out for now. And then finally we need to look at this checkpoint file system here. So this lets you decide whether you want to load or save a checkpoint. So a checkpoint would be the end state of a previous simulation to be loaded as a starting point for your new simulation. We haven't run any simulations yet, so we're going to say no to loading a checkpoint, but we will save a checkpoint file, as it can be useful to have it for later. There is a separate video explaining in detail how checkpointing works, so I'd recommend you watch that if you're interested in knowing how to do checkpointing. So now let's go to the simulation options tab here. So I'm going to call this urea. And then we need to choose the path to where it's going to save these files. So we'll click browse, and I'll go to my simulations folder, and I'll create a new folder, and I'll call it urea. And then I'll select that folder. So now all the output from our simulation is going to be saved in that folder, and it's going to be given the file prefix urea. Now we have some options here for where you want to save the XYZ files, the visualizer files. This is for high throughput simulations, so if you're running a lot of simulations where you're varying some parameters, so if you change these vary boxes here. And if you have them together in a separate folder, it's very useful for high throughput image collection using both Avito or the Crystal Grow visualizer. So we'll leave that as together in a separate folder for now. Now the simulation setup section here, there's one parameter here which is specific to net-based structures, and this is do you want species grouped. As we mentioned on the previous tab about the two urea molecules being the same point group symmetry, then we can treat their interactions as the same. We can also get Crystal Grow to group these molecules together for the calculation. So generally you want to answer yes to this question unless you've got some chirality in your system, where you want to treat some species differently. But we'll say yes for now, because there's no need to consider chirality with our urea molecules. We can set the temperature, we'll keep it at room temperature, and the number of iterations here will define how long the simulation runs for, so how many growth or dissolution events can occur. It's kind of a description of simulation time. So we'll run this for 1,000,000 iterations. Now we can get to assigning memory. So if we want to calculate memory automatically, we can say yes. Or if we want to define the memory size ourselves, we can say no. And then there's an upper limit for the number of megabytes that can be used for the memory space in Crystal Grower. So we'll just leave these as default for now. And then we can choose, do we want to write out a single frame or do we want to write out a movie? So the first time we'll write out a single frame. So now we move towards defining our solution behavior. Our solution our crystal is growing from is defined as a thermodynamic driving force, providing or taking units away from the crystal while it's growing. So we've got a few different modes that replicate normal experimental setups. So for example, mode 3, you'd be growing your crystal at relatively high driving force, and then you'd allow it to drop down to equilibrium. So that's similar to growing crystals from solution and just leaving them crystallize over time. Then we've got another mode, mode 5, which is more like continuous flow experiments. So you grow your crystal at one constant driving force, and then you switch to another driving force at a certain point in your simulation. So this is more like in situ AFM experiments where you've grown your crystal already, and you grow them slowly or dissolve them slowly at a different driving force. So we'll use mode 3 in this example. You also notice at the top there's another additional feature which is excess supersaturation. This is designed for when you want to assign different driving forces for different components in your crystal. So this is more likely to be used with co-crystals or multi-component crystals, like ionic crystals or MOFs, for example. So let's define our starting driving force. We want our crystal to grow quite large to study it, so we're going to set this driving force quite high to make sure that it gets nucleated and actually starts growing. And we'll keep it at high driving force for half the simulation, so 500,000 iterations. And we'll give about 100,000 iterations to equilibrate. That leaves us with 400,000 iterations at the end of the program at equilibrium. So we've defined this period here is our time to reach equilibrium, and this final period here is when it's at equilibrium. So now we've defined our solution phase, we need to define the energies of our solid phase, which is done in net options here. If you remember on the first tab where we loaded in all the interaction types for the crystal structure, that then created this tab where we can actually edit the energies that are assigned to these interaction types. There's also another additional feature here where you can control additional weighting for multiple bonds originating from one species, so multi-dentate interactions, but we'll leave that as no. So we have here some interaction energies. I'm going to leave them as is. I have edited these from the topos file, as topos calculates these based off solid angles. These numbers are usually a lot larger and not necessarily correct, so you'll definitely need to change these values. But these are ones we know are quite good for urea after testing a large number of energies. Then we can go to the crystal coloring tab and decide if we want to color our crystal in layers or if we want to just color it by species type. For this first example, I'll say no. We'll just color by species type. And then we can click Run Crystal Grower and that'll run our simulation. Once the simulation is complete, it'll display a message to say it's completed. And then we can go and visualize the simulation in a veto. So if we go to the file location where we saved the simulation, you can see the simulations are dated year, month, day, and then you have a time as well. So you can always tell which simulation's which. If we double click here, because we chose to separate our XYZ file, this is where our visualization file will be. And then all of our data will be in here. We've also got our GUI simulation data, which we can read back into the program to populate all the boxes we filled during the simulation. So let's visualize the result from this simulation in a veto. Because I said no to layer coloring, we won't be able to use it in this simulation, which is normally in column number 3. So in this example, everything will be colored the same, unless I picked one of the other columns, like column 2. So you can see we have a nice urea crystal morphology. And this is the sort of morphology you'd normally see. So you have the twist in the crystal running in the C direction, and you have all the right faces exposed. So now let's try changing some parameters and see if we can get a different crystal morphology. So we'll go back to the program. And this time we'll try and make a movie. We'll go back to the simulation options tab and we'll click movie here. And we're going to choose to make a simulation of 20 frames. And it's going to start capturing frames at iteration number 1, and it's going to capture the final frame at the end of the simulation, so iteration 1 million. So that means there will be 20 frames spaced equally between iteration 1 and iteration 1 million. So we'll have one frame every 50,000 iterations. So now we can run this simulation again. Now that this simulation is complete, we can also go and visualize that in Avito. So we'll open the XYZ file again. But this time we'll have multiple simulation frames. So you can see down the bottom we've got 0 to 19, so we've got 20 frames. So if we watch this simulation, we can see our crystal grow over time. You can see at the beginning it grows very quickly, and then as you reach the halfway point it starts to grow a lot slower because we're at equilibrium. So at this point the crystal's just rearranging units on the surface. Now let's try and get a different crystal morphology by changing some parameters. So we'll go back to our user interface and we'll go to the Net Options tab. So any changes we make here will have quite a large effect on the crystal morphology. So let's try changing all these strong interactions and make them a bit weaker. So we'll change them from 3.5 down to 1.5. And we'll make a movie again to see how the crystal growth process changes over the course of the simulation. Now that this simulation is complete, we can visualize it in Avito and see how the morphology changed. So we have a movie of 20 frames again. So if we zoom out and press play, you can see the crystal morphology's changed dramatically. It's shrunk a lot in the C direction and it's become a lot more rounded. So let's change those energies back and try adding some additional features during crystallization. We'll go back to our user interface. We'll change these energies. We can either change these energies manually, or we can open up a previous simulation. So I'll open the last simulation we ran with the correct energies here. And if I click the GUI simulation data.txt, it'll load all the same energies back in. So this is really useful for being able to load up previous simulations. You can also save simulation data as you fill in the boxes in the user interface. This allows you to save them to a location so you can call them back the same way we just did when we clicked open there. But we're going to add some additional features here. So if we go to the supersaturation profile, we'll try adding some excess supersaturation periods. So excess supersaturation, as the name implies, adds an excess on top of your existing delta mu mode or supersaturation mode. So it's a lot easier to run in mode 2 when you're doing this. You can set your baseline for your delta mu mode at 0, which allows you to define all your excesses relative to your equilibrium point. So we'll now change our excess supersaturation box from no to yes, and a new tab appears. So we'll go into this tab, and then we can define as many periods of excess supersaturation as we want. So what we're essentially doing here is creating our own delta mu mode with as many changes in delta mu as possible. So mode 7 has 3, but with mode 2 and excess supersaturation we can make as many as we want. So let's for example make 5. And then we can click generate fields, and it'll create 5 delta mu excess periods for us. So first we have to define the lengths of these periods. As we have 5 periods, it makes sense to split them all equally. So we'll make them all 200,000 iterations in length. So 200,000, 400,000, 600,000, and 800,000. And then it will automatically end the last period when the simulation ends at 1 million. Then we can define our driving force for each of these periods. So we'll use the first period as our nucleation stage. Like we previously did, we set it as 100. Then we can start reducing this value, so we can put this down to something a bit lower. So we'll try 20, then we'll halve that down to 10, then 5, and then 2.5. Because we're making many smaller steps, it makes sense here to actually have a longer simulation and capture more frames over that simulation for our movie. So we're actually going to increase these by a factor of 10. And I'm also going to go and increase the simulation length by a factor of 10. And we're going to take 50 frames instead of 20. So I've changed the length of the simulation so it's a lot longer. And changed the number of frames so we can see each period of delta mu excess for a little bit longer and study it more carefully. So I'll run this simulation, but it'll take a lot longer as the simulation's longer and it's writing out more frames. So now that our longer simulation's complete, we can go visualize it in a Vito. If we open the XYZ file and choose the column mapping, then we'll have our 50 frames loaded into a Vito. And those frames will be split into the 5 delta mu excesses that we set previously. So the first 10 frames will be the first period, the second 10 frames will be the second period, and so on. So let's watch the growth process of our crystal. If we zoom out slightly, you can see how the surface is changing as the crystal grows. So the nucleation starts very quickly, and as we get to the lower delta mu excess towards the end, it starts to slow down on the surface. But even towards the end of the simulation, there's still quite a lot of surface nucleation occurring. So let's have a look at another facet and watch that one grow as well. You can see a similar thing occurring here. Still a lot of surface nucleation, but it slows down slightly towards the end of the simulation. So I hope that's shown you a few techniques for using the graphical user interface for Crystal Grower, and shown you a few options that you can change when using net crystals. This is just a general overview of how you use the program. There are a lot more videos explaining in detail some of the routines, and showing some more of the advanced features that you can add during your crystallization. For example, screw dislocations and growth modifiers. But this should be enough to get you started with running some simulations, provided you have your structure file and your net.txt file, which contains the energies for your interactions in your system. These are generated with Topos Pro or Crystal Maker, in combination with our interaction program, and the procedure for obtaining these is detailed in another series of videos.